Okay, so this is the notebook I used to produce the graphs which we have been using in chapter 1. So what we want to do today is, first of all, remember what I've always been saying about Python. When you are using Python, you're not entirely helpless. There is always help around the corner. So first of all, what we want to do is we want to see how we can use the stuff which is available to us to make headway with our problems with the course. So we want to solve nonlinear equations. So how do we do that? So the first thing which we're going to do here is we are going to import. We need NumPy. So we're going to import NumPy. So we're going to import NumPy using the alias np. So normally NumPy is imported using alias np. So after importing NumPy, the other thing we're going to do is we are going to import matplotlib. I want to look increased. Okay, so we are also going to import matplotlib. I don't know how it looks on your end. Okay, so we're going to import matplotlib. So I want things to be as clear as possible. So we're going to import matplotlib, but something specific. We're going to import pyplot, which is a submodule of matplotlib. So we're going to say matplotlib.pyplot. Then we're going to use the alias plot to do that. So that's what we use for doing our graphs. So the NumPy, we use it for doing numerical computation. The matplotlib.pyplot, that's what we use for doing our visualizations. Okay. Next bit is we are going to create a function. This function should be common to you. That's the function we've been working with when we're looking at bisection. X to the power 5 minus 2, x to the power 3 to the power 2 minus 3. So we are going to create a lambda function. This lambda function f of x. So when we do that, I'll reduce a bit. So this is how we create a lambda function. So f, that's going to be the name of the function. Then we say lambda, we use the keyword lambda. Then after lambda, we specify how many variables this function has. It only has one variable, so we specify, say, this function is only going to accept one variable, and the name of that variable is going to be x. Then what is the expression for the function which we are talking about? That's going to be x to the power 5 minus 2 times x to the power 2 minus 3. So that is the expression for our lambda function. Okay, the function which we want to work out. So in this case, that's good. So we run our lambda function. Then we also create our kind of array x, since we want to produce a graph. So we create our array x using NumPy. So we're using the arange function in NumPy. So we specify where we want to start from. We want to start from 0. We want to go all the way up to 2.6. Then we want to move in steps of 0.05. So that's what we're going to do there. So we do that. Then after doing that, next we print the values of x we have produced. Just a minute. Print NumPy array x. So we print our x, or display basically. If you do a print, what you print x. So those are the values of x which we have generated. So with these values of x which we have generated, next, so these are the values of x from 0 to 2.6, but less than 2.6, because it will not go up to 2.6. If you want it to go up to 2.6, we can add a 5 somewhere at the end there, so it actually goes 2.6 there. So it ends up to 2.6 somewhere there. Then after that, we can display the values of the function at each of these x values. What is the value of each of these? What's the value of each x value? Each of these x values at the function x. So we can say here display or print the values of numpy array x at, we can say f of x. So we want to display print the x values at x. This one here we could actually probably just change it to just say x. Same applies here. Makes better sense. Looks better. There. So when you do a print of that, print of x, so this is what we end up with. Those are the values of the function at that particular thing. Okay, so these are the values of the function at those x values. Next bit, we make a plot. So here we'll say make a line plot. So here make a simple line plot of f of x. Okay, so we make a simple line plot of f of x. So using PLT pyplot. So this bit here is going to create the figure, create the plot figure, Here, this line, so this PLT.figure is going to create the plotting figure we're going to need. Then this other bit here, PLT.plot, is going to plot x values against f of x. So here, plot x against f of x. Then here we're going to add the label, add x label. We can just, sometimes it just be fine to do this. Then the other bit, this other one, we're going to add y label, add y label. Then here we're going to add a legend. So this is legend location, we'll say based. This is going to add the legend, then this bit here is going to add a grid, then here we're going to save plot figure, save plot to JPEG file. Then this one is going to show us a plot, show plot. So when you do that, this is what we have produced. So what you have produced is the graph which you saw in your notes of the function f of x at x5, x to the power 5 minus 2, x to the power 2 minus 3, and you get this thing here. Now, at this point, you have to be aware that I will not be explaining too much about whatever is happening here, because you have to recall that we have spent half the year since the term started. Basically, this course was supposed to be finished, okay? But we have spent half a year learning Python so that we can use it for these particular ends. Are we clear?
Yes, sir.
So if you do not understand something which I'm doing, or it doesn't click somewhere in your head, in your mind, say, where does this come from? You have to go back to your notes. The notes which are on Moodle, definitely there's going to be a YouTube link somewhere. If you're having trouble with plotting, then you have to go back to visualization. If you don't understand what NumPy is doing, then you have to go back to the chapter on numerical computation with NumPy, and you have to watch the videos. So when it comes to teaching Python, That bit is done. The only thing we are going to be doing is we are going to be using the Python we have spent the greater part of the year learning, so that we can now solve our problems using a computer, because that's the whole essence of the course. It's not that you have to, yes, you are going to write your exam with pen and paper, but even as you are writing exams with pen and paper, the whole point of the course is that you are able to do these things using a computer. You're able to produce graphs using a computer. You're able to produce your stuff using a computer. Okay, so we have managed to produce our function. We have also managed to produce our our plot. The next thing which we want to do is now we want to use the tools which are available to us. Okay, we want to use the tools which are available to us to solve this problem. So we are going to import something. We're going to import.
So,
yes.
I'm sorry to take you back. I just want to. I'm a bit lost as to the values that come after the function we've defined. You've put 0260 and 0.05. Yes, just there.
This 0 here.
Yes.
Is the start point. Is where the
okay.
That's the start. Then this bit here is where the function is supposed to end. The list is supposed to end. The list of numbers is supposed to end, but it excludes this one.
Okay.
So it only goes up to 2.6. Then this bit here is the step size. The size from 0 you increase by 0.25. You see, so by 0.05, which is what you have here. Then it becomes 0.1, then 0.15, then it becomes 2. So you're increasing in steps of 0.05.
0.05.
Yeah.
Thank you so much, sir.
Okay. We have these things already. Yeah, you have to look at the stuff for NumPy and also on lists and other things. There's a function called arrange when you're looking at built-in functions which come with Python. So you have to look at that. So people have to refresh themselves. Continuously watch the videos, see what stuff is there. Okay. The next thing we're going to do is we're going to import a module. So we're going to import a module called scipy. I don't think we have looked at this, but you're going to import a module called scipy. So import scipy module. Scipy stands for Scientific Python. Scipy module. So I'm going to say import scipy. Then, so a scipy has been imported. Then next I'll try to check what does scipy come with. What does it bring to the table? So list the contents of scipy module. So this way, using dir function. So there's a function. If you open a module, there's a function you can use to see what kind of stuff that module comes with, which is the dir function. It's a built-in function, so it comes with Python, so you don't have to do anything about that. So we're going to say dir scipy. Okay, it comes as a list, very long list, but we're going to print. So instead of listing, we'll print the contents of scipy. We'll do this. When you do a print, things come out better. So we'll say print the contents. Print. Okay, so there's a lot of stuff which comes in. So this basically shows you that we have managed to import this scipy. If you can see this, then you have managed to import the scipy. But that's not the reason why we want to do this. What we want to do, since we have managed to import scipy, we want to ask for help. We want to look at what scipy does. what does it offer, because there's something we're interested in. Okay, so get help on scipy. So we're going to say help. So the help should load. The help file should load. So here's a help file for scipy. It has loaded. So it says help on scipy package. So what does scipy do? Okay. So we start with the name of the module. The name of the module is scipy. Then the description. Scipy. What does scipy do? Scipy is a scientific computing package for Python. Okay. If you want more information about scipy, it's available on this particular link. Someone's microphone is on. Who is it?
Oh, sorry, it's me.
Okay. Next, what are the contents of this module? Contents. Scipy imports all functions from NumPy. So scipy has got everything which NumPy has, and additional packages. Now these additional packages are what we're interested in. One of them. So one of the additional packages which we're interested in is which one is it? It's scipy interpolate. I think it's is it optimize? No, yeah, this one. One of the packages we're interested in is this one. Optimize. So this package, optimization, that it contains optimization tools. You can look for a description somewhere, but we're not going to do that. We're just going to specifically try to get to the optimized bit and see what it has to offer. So we're going to do another import. So we're going to specifically import the optimized bit. So the sub package which comes with scipy, which is the optimize. So what you're going to do is you're going to say import scipy dot optimize submodule. So we're going to say this. So import. So you can have a module like scipy, which is very big, then it contains other modules inside. Like the way matplotlib is. Matplotlib is very big, then it contains a module inside which is called pyplot, which is what we used. Okay, so that's not something which is supposed to confuse you too much. So optimize there. Okay. Alright. Then once we do the import, we can print the contents of this bit. What do we have access to once we do this? So print the contents of scipy dot optimize submodule print dir scipy when you do that, you get some stuff. What are we looking at? Yeah, so what we're looking at, if you notice, is this guy here. We are looking at bisects. That's a module which does bisection. We are looking at something called Newton. There's a lot of stuff. There's curve fit. In this optimizing, there's curve fit. There's another one which is of interest to us in our course. Newton minimum. This guy. This is what does the Newton-Raphson method. So for now, our interest is this guy here. Okay, bisect. So we're going to import this guy, bisect. So you're going to say, is that clear? Any question?
No question, sir.
Okay. So we're going to say import the bisect function. So we're going to do an import. So import. There are a couple of ways you can do this, but I'm going to do the following: import bisect, import bisect from scipy dot optimize submodule. So you're going to say, so if you want to import something specific, you say from scipy dot optimize import bisect. Okay, then we can get help or not by what bisect is supposed to do, since we have imported it in the workspace. Get help on bisect function. So say help bisect. So we get some description of what bisect is supposed to do. So this is the following. This is what you get. Says help on function bisect in module scipy to optimize zeros. So bisect will need the following. Bisect is going to need a function f. Is going to need a lower interval a. Is going to need an upper interval b. Of course, the tolerance has been set. So this bit you don't have to do much about it. But also this bit has also been set. The number of maximum number of times bisect is supposed to run before it stops has been set to 100. Are we clear?
Yes, sir.
So this bit here between the x values. Remember when you're doing you're doing bisection, you have to find the c value, right? You have to find c. You do a plus b divided by 2. And you find c. Between the consecutive values of c, the smallest difference between the consecutive values of c is supposed to be this x tolerance. This is what is called the tolerance between your c values, between two what's supposed to be the smallest difference between the two adjacent values of c. Then this one here is the root tolerance, the value of the function at c. What is supposed to be the tolerance? It's supposed to be smaller than how much? Is that clear?
Yes, sir.
Because these are important, because somewhere, somehow, you have to figure out when you're going to stop. So by default, as you can see, this is the definition of the function. It will need a function f, then you need a, then you need the b, then of course this bit will not need, but this bit has already been set. So these are what we call default values which have already been set. So this bit, the x tolerance has been set, the root tolerance has been set, the number of maximum iterations has been set, our full output has been set to false, but if it has been set to false, you can change it to true. If you want to see the full output, what is everything which needs to be whatever it is. So you get a small description. After that, you get an explanation of what the function does. Find the root of a function within an interval using bisection. So here you're given an explanation of what the function does. Okay. Then the basic bisection routine to find a zero of the function f between the arguments a and b, f of a, f of b cannot have the same signs. Then advantage and disadvantage, you're given an explanation. Bisection is slow, but it's sure that it's going to get you the value. Okay. Then there's a description of the parameters. What is f? F is a function. So we already have a function, the lambda function, which I've created up. So the function is already there. We've created that. Then next, here, what is a? This is a scalar. One end of the bracket interval ab, then b scalar, the other end of the bracket interval ab. Then the other things, x tau, number optional. Basically this is a tolerance in the x values. R tau, number is optional. Again, that's a tolerance in the root. Then this max iter, this is a maximum number of iterations. Then of course there's full output. If you want full output, you can say it's true and stuff like that. Then what are you going to get in return? So this is important. So what you're going to get in return is x naught. X naught is basically a floating point number. This is a zero of f between a and b. So you're going to get a 0. And of course then r is the root result. Basically r is I think the value of the function at that particular point. Okay, and you have some bunch of examples of how you can use your bisection, whichever way you want to do it, but that's fine. So in our case, we have a function which we want to work out with bisection. So in our case, our function is I don't know if I can let me open something just a bit. Model. Any questions so far? I want to open the example which you have in your notes, so we can see if what we did and what we came up with, if there's actually any which makes sense. So what's the minute? Okay. So I'll share this tab a bit. I'll stop share. So you can see we are looking at the example which you have in our notes, which is this one. Okay, so I'll copy this example, just the statement of the example. I'll copy it, I'll paste it in the notebook, then we'll proceed from there. So this is what you're looking at. Okay. Down. Then what other thing do I need to copy? Bisection went on. Bisection method. Example. Just a minute. This is not part of Python, so you can just ignore it for a bit. Okay. What has happened? All right, so that's what you have there. So this function we have already defined, remember? So for us to use bisection, we're going to say bisect f, which is our function. You can say f is equal to f, that's okay. You can do this, f is equal to f, but just putting f is fine. Then our a is, you can put a equals to 0. Then your b equals to 2. Like that. Or before, you can do this, a equals to 0, then you can do this. So f for the function, this function which I've defined as a lambda function there, then a for the 0, then b for the 2. When you do that, then it runs, you get your answer like that. You notice that this answer is exactly what you had. Or you can say bisect f, then you can say a equals to 0, b is equals to 2. Run that, you get your answer. Is that clear? So straightforward. There is already these bisection. People have been doing this thing for a long time. You're not the first people to do this, and they've always tried to find ways of doing it faster, easier. If you look at what we have here and what we found in our notes, if we go to our notes, if I start sharing our notes, we go down, the root we found, here, this is what we found, 1.4961 when we were doing it ourselves. But since it's a computer, you have a computer which you're using, computers have got the advantage that they are faster. As we could only find the answer up to this point, up to there, but a computer can do better. It can do things faster, more, without any time lost, since our computers are faster these days. Is that clear?
Yes, sir.
Any question? Of course, you can try to find out more information, because right now it's only giving you the root. There is no other information which it's giving you. The reason why you're not being given any other information is because if you look at how bisect works, by default, this bit here, if you look at bisects, by default, there is a parameter, this parameter which says full output. This parameter full output has been set to false. So if you want to see more information, then you have to set full output to true, and that's what you're going to do. So if we say true, then we can find out more information about how many times this bisection ran and all the other good stuff on what happened with this bit here. So we can add more information. If we can ask for more information. So we can say, okay, full output, set full output to true. Then when you do that, this is what we get. So you get, as you can see, you get this bit here. This is what you get. It ends here. This is a tuple. So you get your root, which is the answer you're looking for. Then it tells you whether it converged or not. Yeah, converging happened. Then it tells you how many function calls were made, 42, how many iterations, how many times did it run? It ran this much. And what is the root? The root is this bit here. So in our case, our function ran 40 times. So the bisection was done 40 times to get to that particular answer. Are we clear?
Yes, sir. It's clear.
Okay. Is there another question? So this is the easiest way to do bisection. You import scipy, optimize, then from scipy to optimize, you get the function bisects. The reason why we are doing this is because we already know how to how to do our import of modules. If there's a module somewhere which does this thing, you can just go and import that module. Then you look at how you import the particular function you're interested in. Then you look at what the function does. Then you see how you can use it. In this case, that's our bisect. Is that clear? So that's our example number 1. Us using Python to work out a bisection problem. If you look at our notes, if I share our notes, there is also example number 2. Example number 2. So I'm going to copy example number 2, which is this one. I'm going to do a copy. Then I'll come back. So we are going to do these things in class. We work out with pen and paper. We see how the problem works out, how a method is used. Then after that, we see if there is a fast way of doing this thing, like in this case with a module. Then after that, probably we can learn how to, I don't know how much time we have, since we don't have the whole year to do this stuff. We can learn how to actually make your own bisection function, which can be tedious, but the problem is we don't have a lot of time. So I don't know what's going to happen there. Okay, so we have this particular function here. So this function, we want to use bisection method. So the first thing we do is we have to create a function. This function, you have to create it. So we create a lambda function. F of x equals to cos x minus x plus 1. The interval, of course, is between 0 and 3. So in this case, we create our lambda. F is equals to, it can be g, it can be whatever it is you want. We can say, okay, fine, now our function is what? It's g. It doesn't really matter. You can put g here. It doesn't really matter. Are we clear? You can change it to g. It won't affect anything. It doesn't matter. Okay. It's just that by convention we display functions using that. So we're going to create a lambda function, f of x cos x minus x plus 1. So in this case, this is our lambda. F of x is going to the name of the lambda is going to be f. Then how many variables is it going to accept? It's going to accept only one variable x. Then there is this bit here, the cosine function. Now with this cosine function, we are using arrays. So we have to get the array version of the cosine function, and that's what you're going to get from NP, from NumPy. NumPy.cos x, then minus x plus 1. So we run that. Then next bit is you, of course, between we're interested between whatever the range here, minus 1. What did I put? Minus 1, and as the interval is between 0 and whatever it is, but for plotting purposes, we're going to use something else. And 4. So that's what we have done here. So we start from minus 1, we go up to this bit, then like that. Then you print your x array, print your array x. Print.
Sir,
Yes.
I don't know about everybody else, but we're not seeing the notebook.
Oh. I'm supposed to share the notebook. Okay. Print array. Array. X. Sorry about that. Can you see it now?
Yes, thank you.
Okay. Okay, so that's our X values, a bunch of them. Then we print the value of the function. Print f of x okay, so that's the print of f of x. So we've got our x values, we've got our f of x. We can make a plot of this function so we can see what it looks like. Make a line plot, a simple line plot of f of x. And that's what we have here. So this is just a line plot of f of x. That creates the figure. So create the figure and everything else which we talked about earlier. So this is going to be a plot there. So as you can see, our function has got a root somewhere there between 1 and 2. Okay, so we can use bisection. So we can say bisect f a is 0, b is 3, like that. Then we work it out. Then we get our answer as this. At the moment, yes, we're getting along, we're finding our answers. There is mystery in how this thing is being done behind. When other people write a module, they hide the implementation of how the module or their function is doing things. So when you import other people's modules, okay, like in this case, the way we have imported bisection, bisect from scipy.optimize, we are not going to find the description of how this thing actually does the nuts and bolts of the process, how it actually comes up with the root. Okay, if we want to do that, if you want to see how it implements, you have to write the bisection yourself. Since you have got a good idea of what bisection does, and hopefully we can do that. Okay, if you want to see the full output, set that to true, then you get that. So how many times, how many iterations? 41, and that is your answer, and that is your, it tells you it converged. Are we clear?
Yes, sir.
So there is a way you can use. So basically what we are trying to show here is that you can use Python through scipy.optimize to do your bisection. You can find out what the root is supposed to be fast. Any other questions? So those are the two examples we looked at. With with bisection, we can compare our notes to see if the answer is the same. So just switch to the notes. So example number 2, this is example number 2. So that we can build confidence in how these things work. We have this as our answer, 1.265 625 with our notebook. We have 1.28. So our scipy thing went further than our notebook, than the one we did with our hands. No, is it the end? Let me see. Oh, okay. So we stopped somewhere at 1.2 here, but you can see this is not enough. So if we did probably one more, then we could get to 1.28 something. Okay, so we did, in this case, as you can see, with our value of f of x there, we did not go far enough. At least we could have got to 1.8, 1.28 here. So as you can see here, this is our root, the one we worked out in the notes. So you can see from the value which you have here, it's just 0.03. We did not actually go far enough. We could have got something 0.00 something like that, something which is better than what you have. So there is room for improvement on this solution. And yeah, so that's what you have with bisection. Any question?
So, sir, I wanted to ask now if you are doing bisection.
Ati?
If you are doing it by hand, the bisection method, to what decimal place you do leave your answer so that it becomes clear?
In your case, if you're doing it by hand, most likely I'll tell you to do bisection a certain number of times. Maybe I'll tell you do it 5 times or do it 6 times, because I know by then probably the answer is acceptable. So I'll have to be specific. As you can see, bisection can be very slow. It was done 41 times in this case to get to this particular answer. You don't have time for you to do something 41 times. Are we clear?
Yes, we are clear.
Yeah. The other thing, probably after we have looked at how we can do bisection, how we can do what is Newton-Raphson method, and also how we can do second with scipy.optimize. It's also possible that we can also come up with our own. Okay, some things are easier to do. We can come up with our own bisections, but it's not necessary for you to come up with your own bisection, since you have got a good idea of what bisection does. But it's also possible that you want to give yourself some exercise with Python and programming, then we could give that. So we could see how you would write your bisection. If you look at the notes which are already on Moodle there is actually a bisection thing which I've written. There is also must be something on Newton-Raphson method which I've written, but we are going to see how to do that. I will just show and explain. I will get the one from the notes which are on Moodle. Sometime next week when we meet, because this whole thing needs to come to an end next week. Because remember, I have to give you an assignment, so that you need to have the tools ahead of time to know what the answer is supposed to be. Because you are going to work out these things with pen and paper. So you need to have a good idea of what the answer looks like. So whether you're going to use scipy.optimize, say the answer is this, but how do I get to the answer? That's what I want you to practice with pen and paper, because that's what I need for the assignment. That's what I'm going to need for the test. That's what we need for the exam. These other things of you using Python, that's your skill. We examine that through your labs and everything else. Or I can make a lab say fine. Lab number 1 is part A. You write a program which does bisection. Part B, you write a program which does Newton-Raphson method. Part C like this. But the problem is you right now you do not have enough experience to kind of like know how you're supposed to solve this problem. I need to show it. Are we clear? So as I'm showing you, say, okay, this is how you do this, 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 this is how it's done, then things might become easier and easier and easier. So as we go on, then we can give you assignments probably along those lines. For the time being, my interest is to show you how do you solve these problems with Python, with everything which Python has to offer. How do you work out your bisection problem? How do you work out your Newton-Raphson method problem? How do you work out your second problem? Are we clear?
Yes, sir.
Okay, so today we have to end here. We are going to continue on Tuesday. So we'll meet on Tuesday. We're going to look at the Newton-Raphson method, how you do the Newton-Raphson method. And probably Thursday we'll look at how you do your second method. Then of course Friday I can just go through an explanation of the different of if you were to write your own bisection, if you were to write your own Newton-Raphson method, if you were to write your own second method, I'm going to show you pieces of code how it would look like, so that you can study it and you see how it behaves. You can try them out and see if they give the same answers and stuff like that. Okay. But your first option is you should be able to use a piece of code which exists, a module somewhere. If you know about it, then use it. Are we clear? So that you can save yourself time. So today we stop here. The recording will be uploaded tomorrow. See you next week.
Alright, thank you.
Cheers.